In this video, we're going to talk about skewness and the mean, median, and mode, and measures of the spread of the data. So these are in 2.6 and 2.7 of your textbook. So here's just a picture from your textbook showing some data. We have numbers 4, 5, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8, 9, and 10. So we put that in a histogram. We have each interval is just one width, and the value is located in the middle there, how they do the labels. So you can see this shape would be a mirror image. If you were to or fold it in half, it would be the same. So in this case, if you were to calculate out the mean, median, and the mode, they're actually all the same. So that shows that we have a perfectly symmetrical, in a perfectly symmetrical distribution, the mean and median would be the same. So we're going to look at some other figures here, just really briefly, and show how if we have the mean is less than the median, and they are both less than the mode, then it is skewed. This one's skewed left. So that skinnier part is on the left. And this one below, we have the mean is the largest and the mode is the smallest. And we have it skewed right. So that skinniest part is on the right. So then we're going to look at the workbook again. And here's some pictures. So if we have data that's just straight across the board, all the same, it's called uniform. If we have it pretty much symmetrical or symmetrical, it's bell-shaped. If we have it higher to the left part and skinnier, it slopes down, smaller on the right, that's skewed right. The opposite of that would be skewed left. So think of it as where the skinny part is where the skew is. And here's those definitions there. Uniform is they're all going to be the same. Bell shape, your mean, median, and mode are all the same. They're all equal. Skewed right, your mode is less than the median, less than the mean. So it's smaller here. And skewed left, the mean, the brunt of the data is on the right. Mean less the median, less the mode. There'll be questions pertaining to that in my open math that you'll maybe want to have those notes handy to answer. Now we're going to look at measures of the spread of the data in section 2.7. We're going to compare the data. Previously, the measures of central tendency, mean, median, mode measure the difference between the average or typical values between two sets of data. The measures of spread measure the degree to which the data are spread out. So you can look at these three sets of data here. Section A, all the scores are 5 on this quiz. And section B, we have half of them are 0, half of them are 10. So That's interesting. Either people, maybe they didn't come, they didn't know any of the material, and the rest knew it all. Say it's out of a score of 10. So this first section A, they just knew half the material. Section B, half the people knew none of the materials, half knew all of it. Section C is a bit more varied, which is often more what we see. We have a few scores of 4, 5, and then a few of 6. So all 3 sets of these data, if we figure it out and put it into, whatever software, or just crunch the numbers on our own in a calculator, we would have a mean of 5 and a median of 5. Yet the scores, you can see that they're very different in their makeup and how they lay out. So one way to look at the spread of the data is looking at the range, and in that you just take the highest value minus the lowest value, and that can give you some information to see, like with this section A, you would have your range is 0. In section B, your range would be 10, because you'd go 10 minus 0. And in section C, it has more of a normal range. 6 minus 4 would be 2. If we look at these sample of peanut butter jar prices, just find the range of the data set and then kind of just think about what that means. So just pause the video and jot that down. We have $3.99, $3.79, $3.59, $3.75, $3.29. To find the highest, subtract the lowest. Okay, so the range for this happens to be 70 cents. Another way we can assess like how varied a set of data is. Sometimes we can't see all the pieces, or it's just too big a data set. We're not going to be able to eyeball it. And range isn't really going to tell us that much in some cases. So we need to do something called find the standard deviation. So I have an example of how they figure that out mathematically by the formula, and it's in the form of a video. We are not going to use the formula in this course at all. You're not expected to crunch all these numbers. I just want you to see how it is. I will show you really quickly like what it looks like in the book. So in the book, they have a brief explanation of standard deviation and how it's used to determine whether a data value is close or far from the mean. And they have, a variety of formulas here that we'll go through in the workbook. Just how to find a value based on if you know the standard deviation and how many standard deviations away from the mean and things like that. We'll work on that more later. But the thing I want to show you is how to find the standard deviation, and the formulas are a little bit complicated. And you have to do this big chart, and the video goes through it really quickly. It's just related to finance. But I don't expect you to do this. I don't want you to be working out the numbers like that. The main thing to notice, and why we even show this with small data sets, is that you can see we're finding the difference of the data value and its distance from the mean, and then you're going to square it and add all those up and take the square root. So it's just a tedious formula, and we can use our technology. We can use GeoGebra or Staplet, I've shown you before, where we can see standard deviation. There's the population standard deviation, and here is S is the sample standard deviation. Is given just when we crunch our numbers for the in the computer, just like mean is in our 5-number summary. So it's really convenient, and there's really not a reason to have to do it out by hand anymore. So we are going to take a look at the this video clip. I'm going to show you really quickly. So this link that I have in the workbook there for you is it's through Investopedia, and it's all related to finance and how that these things are used in finance context. I just found this video a little bit interesting.
Introducing Ultimate Speed from Comcast Business.
Standard deviation, or the square root of the variance, is a measure applied to the annual rate of return of an investment to measure the investment's volatility. Every time you buy a stock or a mutual fund, you're weighing its expected return against its inherent risk. The past gains or losses of an investment are fairly easy to look up, but gauging risk is a little trickier. Applying the standard deviation formula will show how much an investment's price has gone up or down in the past, and therefore helps in evaluating future outcomes. Take, for example, a security, where we analyze 5 periods of the following stock returns: 2% in January, 7.5% in February, 1% in the next month, 6%, and 1.5% finally in May. To find a standard deviation for a security, find the average historical return, which is 3.6%, and subtract the returns from each month. Square them and find the sum. Next, we divide that sum by the number of observations minus 1. In this case, it would be 4, leaving us with the result of 8.675. Taking the square root of that number, we are left with a standard deviation of 2.9. The calculation can be particularly helpful when looking at similar investments in the same asset class. If one investment has a higher standard deviation than the other, that investment is more volatile. Note that past volatility, or lack thereof, doesn't perfectly predict future returns. A stock that has been consistent for months or even years may suddenly experience sharp fluctuations.
Okay, so I just thought that really laid out there all the math really quickly, but we're not going to have just a few data values. We're going to have a lot. So using the computer is really key. So skipping all the math that they did in the formulas and things, we're just going to take the data from this peanut butter jar price problem, and we'll figure out what the standard deviation is. Once you get the standard deviation, if you just square that, you'll get the variance. So if you're asked for variance in your MyOpenMath problems, then just find the standard deviation and square it. So I've already copied over the data and removed the dollar symbols, and you can pause the video and go ahead and do this in Staplet would be easy to use here. Just to review that this is quantitative data, so it's quantitative, one variable, cost of peanut butter, and then I'm putting in raw data. And then go ahead, begin analysis, and you can see down here we have SD is our standard deviation is 0.261. Okay, so you could just write it simply as the standard deviation is 0.261, or 26 cents is how we would say that relative to the problem, because it's dollars and cents. And the variance is 0.261 squared, and so that is 68 cents. So later we'll look at how we use that. If we know a standard deviation and we know the mean, and we know how far a value, how many standard deviations away from the mean of certain data value is, we just don't know what that is, we can figure it out using some simple formulas. So, and that is something we would just do out calculating on the calculator. But we'll look at that in another section. So here is another problem here to find. We have the weight in pounds and the frequency. This was from a prior example. So once you go ahead and make sure you can do that one, this is set up as a table, a frequency table. So it's easiest to use GeoGebra for this one. So pause the video and go ahead and do that. Show you really quick again to review. If you're careful in how we go ahead and highlight this, and then we can hit Control C. We can do both columns if we're careful, and we lay it out. We have to go across the rows like that, just the first two, instead of trying to run it down, and then hit Control V, and that should work, but just double check it. And then we can go over here to one variable analysis, because even though it's two columns, it's still just one variable. And we can go over to the, we could look at a bar chart or something, but we don't really even need the charts. So I'm going to click the statistics here. Oh, maybe I didn't quite catch. Let's do that. One variable analysis. There we go. We could do a histogram, box plot. Really all we need is to hit the sigma x to get our statistics here. So population standard deviation would be 16.361, but this I believe was a sample. So we're going to look at 16.8976 is our answer. So our standard deviation is 16.8976 pounds. So we could just say 16.9. Let's round that off. Mean is 106.0625 pounds. So I jotted that down just so we could kind of show some things out here. If I wanted to know what the value was, one standard deviation above the mean, I could just go ahead and take that mean, 106.1, I'll just round off, and I could add on 16.9 pounds, and I would get what the weight is, one standard deviation above the mean. So that would be 123 would be one standard deviation above the mean. And if we had wanted to know what two standard deviations above the mean, what the weight would be, we would just then go ahead and do the similar thing, 106.1, but we would take that standard deviation, 16.9, and we'd have to multiply it by 2. And so we would make sure we follow our order of operations, or put everything in our calculator using, oops, that should be 1. We would want to use parentheses here and here. If we're typing into our calculator, we often do that, so we just want to make sure we get that correctly. So you can go ahead and finish that out. And we'll talk more in another chapter about where the brunt of the data lies. In a normal distribution, it's going to be centrally located around the mean. and then it will taper off. Standard deviation, here's some more definitions and key things about that. It's a variation based on how far each data value deviates or is different from the mean. It's always positive. Okay, so sometimes we subtract it off, to get a lower score than the mean. You can see what's under the mean, or sometimes we add it on, but the standard deviation itself is always positive. It's 0 if all the data values are equal and will get larger as the data spreads out. Has the same units as the original data. That's why I made sure I put pounds on there. Can be highly influenced by outliers, similarly like the mean. It is interpreted as the average is the mean, give or take the standard deviation. And just note that the variance is the squared standard deviation. And here's a little chart here, a little graph. So here's how we lay this out. We have 1 standard deviation below, 2, 3. See how it tapers off. So the further you get from the mean, the less you're going to have in there. And so we have 0 is what where the mean is, and then 1 standard deviation above, 2, and then 3. And we're going to look at something called z-scores that will really help us to figure all that out. So we're going to really quickly look at z-scores. We don't use them too much in the course anymore. We used to use the z-scores a lot, but we'll use them a little bit. So it's a way to figure out how far away a piece of data is from the average of a group measured in standard deviations. So it tells us if a data point is typical or unusual compared to the rest of the group, which is useful for spotting unusual values and comparing data between different groups. It's calculated by finding the difference between the data point and the mean, and then divide by the number of standard deviations, and all of the formulas for that below. In real life applications, it could be used for medical evaluations, test scoring, business decision making, and investing in trading opportunity measurements. Traders that use statistical measures like z-scores to evaluate trading opportunities are called quant traders, quantitative traders. What is a good z-score? So the higher or lower a z-score is, the further away from the mean the point is. So it just shows where it lies in relation to the other data. And they're important because it tells you where your data lies in the data distribution. And we'll look at that in more detail. So we'll just do a few quick examples with these z-scores. So I had talked about this, that the formula for a z-score is data point, which we're going to call x, minus the mean, divided by the standard deviation. And z does have a sign. It could be negative or positive. So symbolically, here's how the formula looks. Z equals x minus mu over the standard deviation, omega here. That's if it's a population, but we often have sample. So z equals x minus x bar, all divided by s. So make sure if you are doing this out on a calculator, either use parentheses in here or do this subtraction, hit equals, then divide by s. We got to follow the order of operations properly or it won't come out right. So if you're always getting them wrong, double check that you're entering things correctly in that way. So z-scores do not hold the units. They're just unitless, and they're efficient values to compare statistics or parameters if it's a population from different distributions. So for this example, we'll just see kind of what the z-score is, and then we'll do a few more to compare some different scores. Example 2.27, the mean score on a test for a statistics class was an 82 with a standard deviation of 7 points. If a grade A is 93 points, what is the z-score for an A on the test? So you can kind of eyeball it and think, well, if I added 7, I would get 89, so I need a little bit more than 1 standard deviation, right? Would probably be good. So here's our formula, so always write the formula down. And then we're going to go ahead, I've already filled this in, but if you want to start filling it in, you can make sure you can get that number crunched. So we're going to do 93 minus 82 and then divide by 7. And we get 1.571428, and then dot 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 means I didn't round yet. And then usually we round z-scores to 2 places. So 1.57 is our answer for this. So just, you know, when we kind of figure it out, well, that makes sense because it's should be more than 1 standard deviation, that score. So that's a way we can compare relative to, like, if you got a B or something, how varied is that from the mean? That would be less. Like if I got an 83, it would be a lot lower z-score. So here's one to now compare. Example 2.28, a student, Pat, was done taking midterm. She received a grade of 82 on her statistics exam, where the mean grade was 74 and the standard deviation was 12. I'm even going to split this up a little here so you can see it easier. She received a grade of 72 on her biology exam, where the mean grade was 65 and the standard deviation was 10. Lastly, she received a grade of 91 on her kayaking exam, where the mean grade was 88 and the standard deviation was 6. In what class did Pat relatively score better? Okay, so it's not necessarily just the one she scored highest on, if she's like in keeping with the rest of the class, or how much better was she in which class, like relative to the others in the class. And we use our formula z equals x minus x bar over s. And the first one I've done out for you just so you can see. The stats grade z-score would be, I'd take that 82 up here, subtract the 74, divide by 12, so I get 8 divided by 12. And remember, if you're doing this on a calculator, you want to put your parentheses in. You can use Desmos calculator, is nice, or just any calculator. And then we get 0.666 and so on. So z equals 0.66, and it's positive, so it's above the mean. So figure out, if you want to pause the video and go ahead and do the other two for biology and kayaking and get those z-scores done out. And then check back and see if we can figure out which class you did better in. So here's the answers for the other z-scores. We have, for biology, we have 0.7. Kayaking is 0.5. So the highest z-score shows that this student was further away from the mean relative to the other students compared to her other classes. So that's, in this case, we're looking at as a good thing to be a little further. So that's the course she scored relatively best in. So it's not always going to be like, oh, the higher the z-score, the better. Sometimes it's like, not as good. So you just have to kind of look at the context of the problem and make sure you're taking that into consideration. So one more example for you to try. We'll be done with this chapter. So in a 5th grade class, this comes from the book. Actually, it's just a textbook example. Just because I'm doing it a little bit differently, we're not using the formula, so I want you to see how it lays out in here, and it's a good one to practice. We have this averages of 5th graders, and we have 20 5th grade students, and here's their ages rounded to the nearest half year. So we're going to have to find out some other information. This is just a reminder that for a sample, the a data value would equal the mean plus number of standard deviations times the standard deviation that I was talking about before with the pounds. The first step we would have to do is actually find the mean and standard deviation. You can just use your computer to do that. So go ahead and do that in Staplet. And then for B, you're going to use this formula here and find the value that is 1 standard deviation above the mean. For C, you're going to figure out 2 standard deviations below the mean. And for D, it will be the values that are 1.5 standard deviations below and above the mean, the 2 values that encompass that. So go ahead and pause the video and do that. And you might want to check and make sure your mean and standard deviation are correct. I'll pop that in there really quick while you're working on it. Okay, so hopefully you've gotten that done. I did it in Staplet because the way the data was laid out, it was just easy enough to do. And I have my mean and my standard deviation. Mean is 10.525. I'm going to round to the hundredths place because my one more place than the data would be that. And standard deviation is 0.716. I'd round to 0.72. So you can check that. One thing I did just want to look at really quick, that's a dot plot, but if I put it as a, we'll just say histogram in there, and you can kind of see how this lays out. It's not a normal distribution, but you know, the data is not very varied because they are in 5th grade, and there's going to be maybe, you know, a little bit older kids, but most of them will be around the same age. And so here's the answer here. So use those numbers to find the value that is 1 standard deviation above the mean. And then 2 standard deviations above the mean. And the next question is 1.5 below and above the mean. So pause the video and calculate those, and I'll put the answers up. Okay, so here's the answers for that. We take the mean, add 1 times the standard deviation 0.72, we get 11.25 years. 2 standard deviations below is 9.09 years. Same formula, just make sure you change it to subtract here and change the number of standard deviations. And then the values that are 1.5 below and above is 9.45 years and 11.61 years. So with that being said, always make sure you put your units in there so you remember, and because mean and standard deviations do hold units but not z-scores. We're not looking at those right here. So that brings us to the end, really, of this section. We'll be looking more into distribution of data and how the graphs will lay out in bell-shaped and symmetric. Empirical rule, we'll look at that more thoroughly in future lessons. Have a great day.